All right, so we'll go.
Good morning. We are Team 2, and our senior project is the development of a Formula SAE body. The team members are Diego Quintero, myself, Javier Gutierrez, and Angel Nunez, which is not here today. Next slide, please. Here's a brief agenda of what we're going to be covering today. We're going to give you a brief overview of the project and how we split our entire senior project process into 3 different sections: design, analysis, and manufacturing. And then we'll cover a bit about our project management and the conclusion on what we learned and
Well, the other one, Harry.
final recommendations.
Take the middle one off.
Project
There we
overview.
go. Thank you.
Our senior project was to develop and manufacture a carbon fiber body for the Formula SAE race car. We decided to split the process into 3 different stages, as I mentioned: design, analysis, and manufacturing. And our motivation for this project was based on the results for previous years. The SAE team started last year, and one of the areas that needed the most improvement was the body of the car and their aerodynamics package. And we believe that by making it a senior project, we were able to have a more in-depth analysis of it and improve the overall design for it. This is a picture of the car of last year. Next slide, please. The first decision that we had to take in the design process was the type of platform that we were going to use for the body. There are 3 main different categories when it comes to the body. There are full monocoque bodies, a hybrid monocoque, and a space frame half body. The full body monocoque is made fully out of composite materials, and it has no tubular frame, and it holds all the suspension components and engine parts as well. The hybrid is half tubular frame, half monocoque, and the space frame is a tubular space frame composed with a body around it. Based on the decisions from the SAE team, they decided to create a space frame due to manufacturing process and the difficulty of the entire project. So based on their decision, we were going to do a tubular space frame. This right here is the initial design that we created in Senior 1. Another design decision that we had to take was what material to use for the body. In this competition, the 3 main materials that are used are aluminum, fiberglass, and carbon fiber. Each one of these materials have different advantages and disadvantages. We opted to go with carbon fiber, which is the lightest material and easier to manufacture in comparison with, per se, aluminum. And the only disadvantage from carbon fiber is obviously a little bit harder to manufacture and the expenses related in comparison to fiberglass. Here is a final rendering of our model. We decided to divide our whole design into 3 different sections, which compose of the body of the car, the side pods, and under the body there's the ground effects or diffuser. We did it this way so we could split the work evenly and be able to analyze each of these sections more in depth. Now Diego's going to talk a little bit about the costs related to the project.
All right, so this is the initial prototype cost, what we thought it would cost last semester. And as you can see here, our total was almost $5,000. Now, after doing plenty of research and approaching companies and consulting professionals in the field, we were able to accommodate our budget to the next slide, please, to this. And our total now was roughly $1,200. That is a reduction of almost 70% of the initial cost. What we did is, like I said, we presented a sponsorship proposal to companies, so we were able to get a lot of materials for free as a donation for a team. So we're treating the whole project as if we were a company. We had to do a sponsorship proposal, go to companies, talk to them, try to let them know of our product, of what we wanted to do, and figure out a way to be on good terms with them. So we were able to reduce the sponsorship about 70%. So the first stage of our analysis project was to do some FEA analysis. Even though we're only doing the body of the car, we're not doing the space frame for the car. We want to take this project and we want to leave it pretty much as a handbook for next year's SAE members. So the first analysis was to treat our design as if it were a monocoque. That way, if next year they would like to do a monocoque, they pretty much know how to go about it. We mentioned that some in our projects, the benefits, the cons. With that, we found a maximum displacement of 4.76 times 10 to the power of -6 meters, and a factor of safety of 94.7%. The reason we got that factor of safety is because, remember, we're talking about carbon fiber here, right? It's not like you can go into SolidWorks and put just carbon fiber, because it depends on how many layers you do, how much resin you use, what type of resin, what type of carbon fiber. So what we did is to do some research about the carbon fibers composites that some other teams did, and they had some testing on those parts. So we got some of that material information and we analyzed it. But for next year, our recommendation is to actually manufacture just a test sample and then test that, and then from that part actually get your material properties. Also, we found a torsional rigidity of 17,325. We had a goal of about 1,200, and that's what 12,000 newton meters per degree, and that's what we researched. Because again, we're not reinventing the wheel, we're just trying to improve previous year's analysis. So for our design itself, we took the FEA analysis that the team did on the frame and figure out some of the key points that we can actually mount our body to the car, because we wanted to mount it to points where we saw least deflections. So we were able to pick about 15 points that we were able to mount the body on the car, and it will not be affected as much with the torsional rigidity that the chassis will feel with the suspension travel. The most important part of our design was to do CFD analysis. This, we took our time to do it on the body itself. We did velocity and pressure on both designs. On body, we focused more on velocity since we wanted to get a drag coefficient from the body. So what we did, you're gonna see it later, we did several iterations of the body, and we wanted to take the body that will have the least amount of drag. One of the things about the body is that we were limited to the frame that they had on the car, right? So we didn't want to make too big of a body, because that way we wouldn't be able to be as performance oriented as we wanted. We wanted to keep it light, we wanted to keep it small, so we wanted to pretty much wrap it all around the frame of the car. So we're kind of limited on that. We didn't have too much give. But at the end, we were able to get a drag coefficient of 0.32, which, as per our research, was pretty good, since our goal was around 0.28. Drag coefficient is not the only, or is not the key factor on this design. What we wanted to do is to generate downforce so that the car will stick to the ground and it will make it faster. It will perform better. So by that, we wanted to add a diffuser to the car so that we can increase the downforce for the car. So with that, we found a maximum velocity that we can generate with the diffuser underneath the car of 87.1 miles per hour, and also a minimum pressure of 100 kilopascal. Why minimum pressure? Because as per our research, we wanted to get a slow pressure as we wanted underneath the car, especially underneath the wheels, so that the car will stick to the ground. Next slide, please. So this, again, like I mentioned, these are some of our iterations that we did based on CFD analysis, and on the body itself, it was based on the frame that the team did. On the diffuser, we saw how performing the CFD analysis, we're able to get a really good approach of what we wanted with the fifth and final iteration. Now, Javi will talk a little bit more about manufacturing.
The manufacturing of composites is a very tedious process. It takes a large number of steps, and since most of the work it's manual, the way we did our specific project, we first started with two-pump foam, and we were able to CNC it with the help of the architecture department. After that, we were able to get the different molds and put them together. And when we put them together, we would always get gaps and small areas that we had to repair. So we first had to sand the mold, and then we used wood glue to cover the pores from the foam and fix all the small gaps and repairs that we needed. After that, we used polyester gel coat, which with a hardener would later on become a solid for us to be able to lay the carbon fiber on. But before that, the main priority is to keep this surface as smooth as possible. So we used bonding putty to further on fix the surfaces and smooth out every surface and curvature in the mold. Since it was the first time making composites, we conducted various samples before going big scale with our project. And as you can see here, these are some of the steps that we had to take before laying the carbon fiber. We had to add layers of sealer to cover even more pores, polish it, do about 5 layers of wax, and finally we were able to lay carbon fiber with resin. And here's a final product of the sample that we conducted. Here is a picture of the 9 molds that we had to do the same type of process with it. Now Diego's going to talk a bit about the project management.
So this is a timeline that we set last semester, and as you can see, we're pretty much on schedule. We had roughly about a week or so of delay, and it was because we were dealing with a team and they had some problems with design. Also, on this table, you can see the breakdown of responsibilities as we approach this project. Next slide, please. So for the conclusions, like I said, we learned a lot from it, since we haven't done any composites work from this. Mostly, our recommendations are on the manufacturing stage, since you have to do a lot of research, you have to consult it with a lot of professionals in the field, because you're dealing with chemicals, you're dealing with, type of materials are really specific and they have to have the specific quantities when you're mixing them together and all that. Some part of our global learning was that we had to use American units because our manufacturing of the foam, the machine was set in inches, so we had to do everything in inches. Also, since we're dealing with an international competition, we had to abide by the design and the manufacturing by some rules, because we have to pass technical inspection in order to be able to race. Some of the acknowledgement we want to thank our sponsors for everything, donating materials. Some students here collaborated a lot with us, our faculty advisor, and some other professor. Again, the entire SAE team. Any questions?
All right, what's the time there? 18? 16. This week, just a little bit. That's better, thank you. All right, very good. I don't have a lot of criticism. Maybe on the GLI, maybe you could say a little bit more.
Okay.
Your project management slide, bring that back, please. The fonts, I'm wearing some binoculars here and I still can't read it very well. So you may want to break that up into 2 slides and make the project management one, the breakdown responsibility another one, and increase the font size.
Gotcha.
All right?
Yep. Right on.
Other than that, excellent.
Thank you very much.
All right, give them a nice round of applause.
Here's a test sample over there.